For billions of years, the universe followed a simple recipe. Particles combine into atoms, atoms build stars, and those stars forge the heavier elements that make up oceans, mountains, and living creatures. Naturally, we assume the weight of everything around us comes directly from the physical pieces that compose it. If you want to know where your own mass comes from, you have to look deep inside your atomic nuclei. The vast majority of the weight in ordinary matter is provided by a single type of particle, the proton. This diagram shows a proton made of 3 quarks, 2 up and 1 down. Adding their masses should equal the proton's precise mass. But actual measurements show these quarks account for a vanishingly small fraction of the true weight. The numbers refuse to cooperate. Somewhere, nearly all the mass is missing. If a proton is built entirely out of quarks, and those quarks have a known mass, the basic math of reality appears broken. To find the missing weight, we look past the particles and observe the environment inside the proton. Those 3 quarks are moving at enormous speeds. They are held together by the strong nuclear force, which is carried back and forth between the quarks by particles called gluons. But gluons have a unique property. Unlike photons, which ignore one another, gluons actively interact and collide with other gluons. This creates a wildly dynamic system. Gluons continuously collide and exchange. Virtual particle pairs constantly flash into existence, only to immediately annihilate each other. The deeper researchers looked, the less the proton resembled a tiny static billiard ball. Instead, it operates as a relentless, turbulent ocean of flowing energy. This chaos is where Albert Einstein's most famous equation becomes essential. E=mc² establishes that mass and energy are connected. We usually think of that equation moving in one direction, mass becoming energy, like in a nuclear explosion or a burning star. But the math works both ways. Energy can also become mass. What if the missing mass isn't in particles? We calculate the kinetic energy of quarks, combine it with energy in gluon fields, and factor in quantum fluctuations. These energetic forces account for 99% of the proton's total mass. This forces us to rethink what mass actually is. The physical matter inside your body and the world around you largely does not originate from solid particles carrying inherent weight. It originates from energy trapped by the strong nuclear force. When you step on a scale, you are primarily measuring energy that has become permanently confined within your atomic nuclei. The mass of every human who has ever lived, the mass of the mountains, the mass of the oceans, this entire planet, and the stars above our heads. Most of the stable matter we interact with exists simply because free-flowing energy became bound into stable, microscopic structures over the history of the universe. But this leaves us with a lingering question. Why does the strong force generate exactly this specific, precise amount of mass? The math governing quarks and gluons is called quantum chromodynamics, or QCD. It details how the strong force operates, but deriving the mass of a proton directly from these equations is extremely difficult. The calculations are so demanding that researchers rely on massive supercomputer simulations just to attempt reproducing the mass of ordinary matter from first principles. Yet with every improvement in our processing power, the simulations confirm the same reality. The weight of the everyday world emerges entirely from these complex subatomic energy dynamics. Our solid world is built from frozen patterns of energy. The deeper we look into matter, the less physical matter we find, leaving only pure energy organized into form.